Alright, so hello everyone, sorry for the problems in the past. My name is Peru, a member of Team 19066 AICitizens, and today I want to present about a few less talked about topics and also consistency and reliability. So first of all, what does it mean to be consistent? Usually consistent robots and consistent performance, because that's what we are actually talking about, means as it says on the slide, there's small differences like every match, in points. You enter a match and no matter the teammate, no matter the opponent, you score close to the same amount when it comes to you, no matter your teammate. Usually FTC teams like to talk about this statistic called OPR, which does mean consistency. It does favor that. It means it's just a measurement unit for how many points you brought into the match. And this way, a team is consistent quite easily based on the OPR, but it's not the best way of measuring. It's not perfect. Nothing is perfect. It's just a good way to measure it. Also, because consistent performance means doing the same thing no matter the teammates or no matter the opponents. That means that the drivers have to know what to do in any case or scenario or any possibility that's gonna happen. They have to quickly adapt, and this way they can score the same. Now, there's a difference between consistent performance and reliability. When we talk about reliability, it means more of the robot, more on the technical side. Mechanisms, as you can see, rarely break. We don't face many problems, and whenever we do face problems, we already are prepared to fix them. We know what we need to do to repair the robot. And also, there can be both mechanical and software methods to increase reliability. It's not all about having the craziest software scheme, finite state machines, fail safes, and nothing mechanical, just fixing everything in code or having the best mechanical robot that barely needs any code. It's a combination of both in the end. As we can see, there is a balance between complexity and reliability in robots, and in parentheses usually, because as we can see here, some teams did manage to make great robots in their season and managed to make them complex and reliable. They didn't focus on adding complexity to add degrees of freedom to be able to place from anywhere on the map, on the field. They added complexity to actually increase reliability in some way or another. But as naturally as it goes, reliable robots usually are simple, and simple robots can usually be made reliable very easily, in just a short span of time. Here's an example, one of my favorite, of a simple robot that managed to have the same performance all over again, have a reliable, everything was reliable about the robot, it was hyper optimized. Now, when it comes to reliability, the most important thing, as stated here, is time. Time is one thing that we as First Robotics and First Tech Challenge competition members don't have, because we started season in early September. Some regions actually go to states in January, February. Romania does it actually quite late. But there's not much time that we have to use to make a reliable robot, and so we need to spend it very carefully, and that's why usually simple robots are optimized. But there's a very good part of the consistent performance that is driver's practice. Something I've seen a lot of teams not pay attention too much is allocating enough time to do driver's practice. They don't drive enough, and by driving they can actually find problems with the robots, automate things to be faster, and also a concept that we'll talk about later, muscle memory, which is actually really important. Practice, as I said, influences uh, the robot quite a lot mechanically and software and any other way you can think about it. We actually spent a lot of time this season, for example, our team, just driving around the robot and seeing what can be improved. It wasn't just a way to test things. We didn't just put the robot on the field and just press the intake button and see if it was able to intake pixels easily. A good way to think about this is instead of just testing the same spot, you would test how it would intake when you are moving at different speeds or going back and forth. It's about how the robot is gonna intake the pixels, for example, in center stage, in the real match, how it's gonna do a task in a real match instead of how it's actually gonna do it just as a test. That's how you actually test mechanisms, to iterate on them, to see what can go wrong and what can go right. When it comes to how much driver practice is required, there's no limit, as there is no limit for mechanical design, software. It's about as much as you can do, as much as you can get. A lot of teams try to go for complex robots and push their deadlines as close to like a competition, an official competition, as much as possible, and end up going there and doing drivers practice in the actual official matches, which is not a great thing. You always want to have a lot of time to practice driving, to practice to see the robot work, to find flaws and quickly fix them and make the robot more reliable and in the end have a more consistent performance. And like I have a graph here, as you can see, the more time you spend, the more diminishing the results are gonna get. Like you're not gonna you're not gonna find the same amount of problems like in a linear time. You spend 1 month, you find like 100 problems. You spend another month, you're not gonna find another 100 problems because you're fixing everything basically. You're hyper optimizing the robot. And it's not something that you do only once. As I said, you have to do it constantly. You have to make a mechanism, test it, drive around, see how it works, change one variable at a time, and do it again. Test the robot, drive a lot, and some teams actually do give just bare drivetrains to their drivers to drive around to get a good feeling about the splines, the complex movements they're gonna need to make to avoid robots, or in this season, for example, the center stage, the truss itself. And now the important subject I want to talk about is muscle memory. This is a subject I really haven't seen talked about much, but it's actually really important. For example, as I said, there's a difference between simple and complex robots. Well, complex robots are not gonna give you the same amount of time to drive around to get that muscle memory in. Usually with simpler robots, teams just drive so much. At one point, they can drive blindfolded. You just know exactly how you need to drive around the field, where you need to do each task, what splines to do, how to avoid. And even some teams that, for example, use float on their drivetrains, so basically preserving inertia, they don't stop, they don't brake. They know where to get their hands off when to get their hands off the controller, and the robot is gonna stop exactly where they want, having this fluid motion, this fluid movement on the field. You can actually see very well which teams spend time training for muscle memory and which haven't. And actually, it does influence designs mechanically quite a lot. One thing I want to talk about, I'm gonna take actually, for example, center stage, of course. I want to give an example as to Overgame. When you can usually see, if you look deep enough, you can see robots that have angle slides that are further in, for example, a 30-degree angle between the tiles and the slides, or actually vertical slides. Now, what this is gonna do in the end is actually increase the amount of drivers practice needed for a team to gain this muscle memory to be fluid, because as you can see here, for Overgame, you're forced to place from anywhere around the square. Now, be careful, I'm not saying you can place from here anywhere on the backdrop. Like from the front of the tile, as close to the backdrop, you can only place down. It influences where you need to stand in the like close to the backdrop quite a lot, just based on the angle of the slides. Some vertical slides robots can't even like place on the backdrop at the top because they need such a large horizontal extension. And Overgame robots usually again need to pay a lot of attention to this. That's why it's quite a good idea to take into account how you're gonna need to place things, how you're gonna need to do tasks, how they're gonna influence. And for example, the 60-degree angle between the tiles and the slides this year, that was parallel extension to the backdrop, was the best idea because you would just be in this line here and you would be able to place on the backdrop no matter the height you wanted to place at. And this way you knew if you wanted to place like on the left, for example, you would just drive to the left of the line and that's it. You just extend no matter where you want it to be. Muscle memory is really important, and as I said, it influences consistent performance quite a lot. It does influence design again. And just a quick explanation on software fixes, which aren't always the best, but they are required to have reliable robots and to achieve the consistent performance in the matches. It's failsafes. Without failsafes, as you can see here, you can end up in a spot where your robot is uncontrollable. A single mistake, for example, at the start of the match, can simply block you, can simply disconnect you. You cannot do anything further, and that can cost you the match. Or maybe it happens at the end and you don't lose that many points, but it's still worth taking a look into fixes. There's also examples when teams wanna go to a spot, intake something, and they're gonna wait until they intook that specific game element, and they don't actually intake in the meantime because they just don't, either one sensor breaks or actually didn't intake, for example, a pixel this year, and the robot just stops and doesn't go back to parking to save points, or outtake the pixels and intake them back again. All of these problems can cause issues, can cost you points, and even the entire match. So it isn't that easy to implement failsafes, but with them you can save yourself from any case that the robot can end into, from any problem, and this way you can increase reliability, and a reliable robot can lead to a consistent performance really fast. That's why you do need to take into account software fixes too. It's not all about the mechanical side. Sure, making a reliable robot mechanically is very great. It's like 50% of the trip there, but then you need software. You can't just use like set power, for example, and then magically think, oh, I took pixels, I'm gonna transfer them into my mechanism, and I know it's not gonna happen because I added a lot of delays that waste time. To increase performance, we need to get these fixes in so we can save time in other places. Well, that concludes my presentation on reliability, consistency, and the subject of muscle memory. I'm sorry again for the problems in the presentation itself and for the reason I had to record this. I was Peru, thank you, and have a nice night, day, the continuing presentation. Bye.